Good morning. How's it going? I'm alright. The weather is amazing. Somehow my ankle is still swollen, so running has not been as fun as I would like it to be. Clark, how's running going for you? You able to like get out and enjoy the weather and stuff? Staying fit? Nice. You know, it's not like you're getting within 6 feet of them, so it really shouldn't be a problem. The great outdoors is large. See, my problem is different in Crawfordsville. They just kind of like, I don't know if you guys experience this much being on the team when you guys are like out running. Maybe it's not as big in packs, but just getting like jeered at in general, just because I feel like people are not super accepting of the whole short shorts, shirtless thing for whatever reason. All right. More people are drifting in. Okay. So, few things logistically to start. Oh yeah, of course they do. I didn't get that much in Virginia, like ever, but back home in Indiana, absolutely get that a lot. Okay, so few general comments. So there's that little like reflection thing. It really shouldn't take that long. The reading itself, I mean, should take like no more than 5 minutes, but like the writing obviously will take a little bit more. This is different than our usual reflection, right? It's a reflection on that little short essay that I linked you guys, and in general, that book has just like a lot of cool stories. And I think it's worth reading, especially as I think we're probably hitting the time in the semester where even if we were in class together and talking about everything, then we'd probably still feel like we were hitting the wall a little bit. And when you toss in all of the other factors going on right now, I'm sure there's probably some struggle with motivation, some struggle with understanding, and in general, I imagine things are a little bit challenging right now. So this is due Friday at the end of the day, so like 11:59. And that's really just like your story, or if you feel like you don't have a story or don't relate to that, then it can just be like reflecting on how the class has gone so far and how you might view it when looking back years from now. And this came about mostly because I was just kind of thinking about the test and like what the goals are and stuff. Right, we also have test corrections. In general, like I mean, I'm offering this mostly because I know a few people will be disappointed with their scores, um, and because the goal is really like learning at this point, and so I'm fine, giving points back if I feel like you're truly understanding the things that you don't or didn't show an understanding of on the test. And so I think test corrections are useful. So those are also due by Friday. So I'm pushing a problem set back like until probably next Friday because you guys have enough to do this week. So test corrections, remember you can get like quarter points if written, and for those who had a little lower score, so if you're below 60%, then you can get a third points back if you do oral corrections. So there, we can either meet on Discord, we can meet on Zoom, we can do something one-on-one and really like talk through the problems. And I think that can be a lot more useful. That's usually how I did it in the past, but just like time-wise, that would be a lot if everyone was doing those, especially for those who don't have many corrections to make. It would probably just kind of feel like a waste of time. But I tried to give a little bit of feedback on the test, but I tried to give not too much feedback so that you can really like think about that and see if you can get the rest of the way, as opposed to just like reading solutions. So that's the plan. You can talk to me about these, and that kind of leads into the next thing I wanted to talk about. So these problem sets were on average terrible. I think a lot of people either started them too late or simply just didn't ask questions when they had questions. And I know that in general, like motivation might be challenging when you're at home. I know that I struggle working from home in the same way that I can work at the office. And I know we have like the pass fail possibility, and I also know we only have like a month left, and there are all these factors. But I hope that you're still like committed to really learning this stuff. And I mean, if you're math majors, then ideally you're here because you really want that. And so when you're doing these things, one, like use me and use each other. Like our Discord is a ghost town, and I think you guys really aren't taking advantage of Discord in the way that I hoped you would. We have the working together voice channel and stuff. You guys can just text in the general chat, right? Like, hey, is anyone working on the problem set? Do you want to like hop in the voice channel and we can talk about it? And then you guys can collaborate, right? In some ways, this might be easier than working with people on campus if you were not inclined to do so before, right? Like maybe you had to like walk over to the library to work with someone. You just want to work in your room or whatever. I mean, you guys are all just in your rooms at this point. So, I mean, yeah, utilize each other, utilize me. I had maybe 3 or 4 people ask me questions, and none until like Thursday, maybe like one person before Thursday. You you've done 3 of these before this one. Like, they take a while. Yes, I tried to give guidance through this one, but at the same time, it was still going to take a while to write up. You should start early, and then that will allow you to ask questions. Also, a few people turned it in like not nearly complete. The goal is not to like turn this in by the deadline and be like, okay, I turned it in by 5. Like, I hope that your other professors are being flexible, and like I'm also willing to be flexible with this. Like I realize that situations are not ideal, and maybe you have a bunch of siblings at home that are driving you crazy. It's hard to do work in a reasonable fashion. Rather than just turn in half an assignment, just ask for more time. I mean, the worst that can happen is you turn in exactly that because I said no. But more likely, I'll be flexible with you and give you a little bit of extra time, and then ideally you can ask the questions that you have on the problems you're stuck on. I just don't think there's a reason for that. My goal is for you to learn, not for you to like turn things in at 5 p.m. like do or die, right? Like, I mean, yes, punctuality is great. I would like you to learn that skill. However, abstract algebra is not, its main goal is not punctuality. The main goal is learning algebra. And so I would encourage you to do everything within your power to work toward that goal. And don't be afraid to ask for help, ask for an extension. I'm happy to talk on Discord. I'm happy to talk on Zoom. That's what I'm here for, okay? Mindset of high school and select few. Yeah, I mean, working together is definitely not cheating. Now, just like using the same overleaf file and like copy pasting each other's solutions is cheating. But yeah, I mean, just talking about problems is absolutely not cheating. I mean, we're in an IBL setting, right? Like, the whole point is to try to figure stuff out, and like math is best done collaboratively. Yeah, that's a fair point. I definitely want you to try to shake that mindset. I mean, math is very, very hard if you make it a lonely pursuit. That's true at any level. You know, when you're a research mathematician, yes, you will write papers on your own, but a lot of them, a very high percentage, are collaborative, right? Very few are solo authored, and so like this is something from this level to the very highest level. Like I think working together is the best way, not just to learn, but also just to like actually do productive mathematics. So yeah, I would really like to see more of that from now on. And so I did tell the people who maybe turned in things that were incomplete or clearly didn't spend enough time that like take another couple days. I'm happy with you resubmitting it and not taking a huge points hit, and then hopefully learning more from the problem set than you currently have. Okay. Any questions on stuff? That was, I guess, more time that I would hope to take out of the start of class, but I think that's just important stuff to say. So yeah, any questions for stuff moving forward? Okay. And I didn't get too many responses on the straw poll, but it seems like most people are okay with Twitch. If you do feel strongly, like maybe I'll put the straw poll in chat after as well. But it looked like we're probably going to stay with the status quo. Okay, so let's finish up talking about symmetric groups. So today we're going to talk a little bit about alternating groups. So I didn't have you look too much into this. I'm going to kind of talk through this. You guys focus more on the cosets. I didn't want to give too much over the weekend when you had the project outline to think about, and maybe you were still working a little on the problem set or something. Either way, you had a lot to do recently. So alternating groups, we're not going to spend a lot of time on this. I'll probably make like a problem set problem on the next one about this a little bit. These are very important examples. So we don't know what simple groups are yet, but alternating groups are kind of really nice examples of simple groups. And in general are kind of, they show up a lot in group theory. And so like, what are alternating groups? Well, to define those, we need the notion of even versus odd permutations. Right, so permutations, just the elements in Sn, right? Choose your favorite n, maybe make it bigger than 2. So ideally, you saw in S3 that no matter how you represented these things, you would get the same number of transpositions, right? Last time we said that all of our cycles or products of disjoint cycles can be represented as products of transpositions, and specifically adjacent ones. So, this guy, for instance, was 1, 2, 2, 3. Let's look at this one, though. So, like, this is 1, 3, 3, 2, or 1, 3, 2, 3, if you like to, write it with the smaller one on the left. And, if you rewrite this and write 1, 3 is not adjacent. So what if I rewrote this in terms of adjacent? So remember last time, like 1, 3, we do the climbing and descending, right? And so this is 1, 2, 2, 3, 1, 2, 2, 3. And note that both of these guys, right, this is 4, this is 2. They're both even. And it turns out that this is not a mistake, and you can check some other ones as well, right? So like, what about just a single transposition? So I mean, you can obviously write it as 1. It already is. You can also do crazy stuff like, just do and then undo before that, right? But the point is, these are both odd, right? 1 and 3, both odd. This one, both even. Turns out any representation of a single permutation in terms of transpositions will always have the same parity. So like, if it's odd in one representation, then any representation of it will have an odd number of transpositions. And so this is a really useful thing, and we'll kind of show why. So I only had you read through. So that was like 103, right? Or 102, sorry. 103 was basically if you have a product of transpositions. So if say sigma 1 down to sigma k are transpositions, and their product is the identity, then k is even. Now the proof was kind of long and a little bit technical, but you won't go too far astray if you just think of the following intuition, right? So like every transposition is like switching two places, right? And so the idea is if you get back to the identity, everything you did, you had to undo. Now that doesn't mean that every time you see a 1, 2, you had to get another 1, 2 necessarily. At least it doesn't have to mean that. But that is kind of the basic idea, is that anything you do, you have to undo. And so that's why you're never going to end up with like an odd number of things. And it's that idea that is actually at like the crux of like the 15 puzzle, which was a project that I put on the table for people to try. So the 15 puzzle is all about kind of the alternating group in terms of like what are positions that could be solved. So, okay, why is this useful? So I wanted to kind of talk through this one. I'm not going to do like everything on this kind of last page of stuff, but just kind of hit the main results for the alternating group. And so basically 104 follows from this. So this is the statement I just made previously. So if you have any permutation in the symmetric group, then every single, I can spell single, representation of sigma in terms of transposition has the same parity. And by parity, all I mean there is even or odd. Right? So every single one will have the same. So if you can do it once with an odd number, then any other representation still be odd. Same with even. Okay? And so that's kind of what we were seeing up above, but obviously like looking at it in one case in S3 doesn't prove it. So how do we prove it in general? Well, this is going to look a little bit like uniqueness. Okay? So basically, right, it would suffice to show that if we have any two representations of potentially different lengths, then they're going to both have the same parity, right? So we just look at 2. So let sigma equal sigma 1 down to sigma k, and also tau 1 down to tau l be two representations in terms of transpositions. Representations of sigma, I'll say by transpositions. Okay? So basically what we want to show is that if k is odd, then L is odd. If k is even, then L is even, right? That they will always be, well, those are both if and only if statements, that they're always going to have the same parity. Well, somehow I need to use a product being the identity. Well, if you have these two things, they should be equal to each other, right? Because they're both representations of sigma. How do we turn this into something equals the identity? What do you guys think? How can we turn this into blank equals E? If it's not obvious because of the notation, if you saw G equals H, what would you say equals E? Because that's basically the situation we're in. Yeah, GH inverse, sure. So that means I'm just going to multiply by this guy's inverse. But we know this inverse, right? We know how to do inverses. It's socks and shoes. Whoops. Tau L inverse, tau 1 inverse. And all of these are transpositions. So what is tau inverse? It's itself, right? Because they're all just simple transpositions. So what we really just wrote is this. And these are K plus L transpositions. Well, now we can use 103, right? Because we have a bunch of transpositions whose product is the identity. So you use 103, and we get that K plus L must be even. Well, what does that mean about K and L if their sum is even? Yeah, they're both even or both odd, right? Because an odd plus an even is odd. So thus, K and L are either both odd or both even. And that's all we needed, right? Because, you know, we say for every, but like if you know one and then it has the same as any other one, then we've shown everything. So, yeah, that's very useful. And so this allows us to give a definition. Sorry, this is not a transposition. A permutation is even if it can be represented as a product of an even number of transpositions. And I should just put odd in parentheses. Right, so it's the same definition for odd number of transpositions. And notice we just say if it can be represented like once as a product because we know that by 104, if we can do it once, then every single representation will. And so that's why this is like well defined. Okay, so essentially this would mean like 1, 2, 3, for instance. Right, the second I know I can write it as 1, 2 times 2, 3, I know this is, because 2 is even, this is an even permutation. Okay. On the other hand, obviously every transposition itself is odd because it by itself is just written as one transposition. Okay. So the alternating group AN, now we have yet to show this, but this is a subgroup, is the group of all even permutations. And AN is called the alternating group. And specifically for N, like the alternating group on N letters, but yeah. Okay, so that's why we needed this definition. We wanted to be able to define this group as all even permutations. Now, can you see why we would not want, so for instance, I did not tell you that there's some other group of the odd permutations. Why? Why is the set of odd permutations not a group? Can we see why? There are several things wrong with it. Two odds make an even. Yeah, so it's not closed. Odd plus odd is even. It also doesn't have the identity, right? So E is like 1, 2 times 1, 2, or you can just think of it as like 0 transpositions, right? It's like the empty word. But either way, it's even. And so if you don't have an identity, well, you're screwed there as well. So yeah, like a lot of stuff goes wrong here. Its inverse does exist and is odd, but that's like basically that and associativity work, but closure and identity do not. Yeah. So why is AN a group? Well, so again, associativity just works, right? Because we know that function composition is associative. So we're good there. It's still, right, that's inherited. It's a subgroup of Sn. So like that's inherited. Is it non-empty? Well, yes. So we showed that E is in AN. E can be thought of as, again, like the empty word, which is 0 transpositions, or 1, 2, 1, 2, which is obviously 2 transpositions. And then, yeah, you guys already kind of saw what's going, what didn't work for the odds is going to work for the evens, right? Because if you have sigma and tau in AN, then this means I can write sigma as this product, tau as, say, this product where K and L are even. Well, then sigma tau, you just smash them together, right? And that's a representation of that guy, and K plus L is even. So sigma tau is also in AN. So it's closed. And then the last thing would be the inverse, and we've already talked about inverses too, essentially in that proof for 104, right? So, if I have this guy, then sigma inverse is going to be this guy. Just reverse the order, and again, they're all transpositions, so that's why I dropped the inverses. They're equal to their own inverse. And, well, if K is even here, well, this is still K. And so it's still even. So sigma inverse is also in AN. And so this is really nice. It's a cool group. What do you think its order is, if you had to guess, right? So we know that the order of Sn is n factorial. What do you think the order of AN is? Any thoughts? Yeah, you just divide by 2. Now, you can't just say, well, even, odd, that's 2 things, I divide by 2, boom, I'm done. You really have to show that there are the same number of even transpositions as there are odd transpositions, right? So basically this follows from a fact that there are the same number of even and odd transpositions. Permutations. So I will probably have you do this on the problem set, but I'll tell you the map. I mean, I say it in like the footnotes of that page anyway. But essentially, you go from AN, you just define a map, right? Because to show that they have the same number of things, it suffices to show there's a bijection, because then you can like pair them each up, like 1 by 1, and just pair them off, there's the same number. And so you can go from an even permutation to an odd permutation by sending sigma to 1, 2 times sigma. I mean, clearly, if this was even, this is going to be odd, because all you did was just add 1, right? So even becomes odd. And then you just have to show that this is, in fact, 1 to 1 and onto. And it's not too bad. And then that tells you exactly what the order is going to be. And so we'll talk more about this when we get into it with cosets here in a second as an example. But basically this means that there are going to be exactly two cosets of an in Sn. Okay. Alright, and so one last thing that you should probably know would be some examples. So we kind of saw a pattern, right? Like 1, 2, odd. 1, 2, 3 was even. What do you think 1, 2, 3, 4 is going to be? Or maybe a general K cycle. So first, 1, 2, 3, 4. Do you think this is... In fact, you really only need... We don't have Lagrange's theorem, Mark. But yes, that would be great. We're getting there. We just defined cosets. Or will today. So you need those. Yeah, so 1, 2, 3, 4. Yeah, that's going to be odd. And we can do that, right, with our way of last time. We can do it with 3. So what do you think the general one? This is going to be odd when what and even when what? If you see the pattern. Yep. So it's odd when K is even. An even length cycle will give you an odd permutation, and an odd length cycle will give you an even permutation. And then you can leverage this to get any permutation, because if you write something in terms of, say, sigma is sigma 1 down to sigma m, where these are disjoint cycles of length k1 down to km. So here, not transpositions, but disjoint cycles, right? So, I take something like 1, 2, 4, 6, 3, 5. I look at something like this guy. So this one is length 4, this one is length 2, and so this guy is odd, this guy is odd. And so what should you end up with? What do you think? Or, wow, I'm sorry. That's, I'm not insane. Okay, yeah. Even number of elements, yeah. And so when you put them together, right, you have an odd plus an odd, so this should be even. And basically, that's what you look for. So if you're looking at disjoint cycles, you just want to look at the parity in the end. Right, so you just want to look at each one individually, and then you'll be able to break it down, odd plus even plus even, odd plus odd, and stuff. And you basically know if you have an odd left alone and then the rest can be paired up, odd with odd and even plus even, then it'll be odd. Otherwise, if you can always pair an odd with an odd and an even with an even, or just have an even by itself, I guess, then it will remain even. So it's a nice way to be able to break things down. Okay, so we're about to get started with cosets. So that'll be a change in gears. So are there any questions? I know this was somewhat fast, but that's because it's mostly going to be like an example. It's something you should see, but it's not something we're going to go super in depth with. But are there any questions on the alternating group? Okay. And by the way, like a really quick way to do this in general, right, is you would look at each of these like mod 2. So like if it's an odd, you would just put like a 1 here and a 1, and then just look equals 0 and z2. And so like your evens are your zeros and your odds are your 1s. And so basically you're just looking at adding up all your cycles, whatever this sign is of it. And if it ends up as 0, then it's even. If it ends up as 1, then it's odd. that would be the best way to do it, because the sign homomorphism is actually super important. We'll talk about it more later. Okay, so cosets. So what we're working toward is actually the theorem that Mark up there mentioned. So we're working towards Lagrange's theorem, right? So our goal here, and our goal is a little broader. I mean, cosets are very broadly useful, but this is one of our like big results in class, is Lagrange's theorem. And it basically says if the order of G is finite, and you have a subgroup, then the order of H divides the order of G. And we've seen this, right? Like in every single example with finite groups, that any subgroup has an order that divides the order of the group. And, you know, I tried to draw your attention to that very, very early in class. And it's followed in every example, and that's because it's always true. And this is the theorem that actually says that. Okay, so we'll finally get this result that we've kind of noticed along the way. And specifically, we also know that when you do divide, this thing you get is the number of, it doesn't really matter which one you choose, but I'll just say left, because that's usually what we'll use, left cosets of H in G. So you'll actually be able to use these cosets to figure out, well, one, they're integral to the proof, and two, this is kind of the result that, like, you know exactly what that factor is, you know, exactly what multiple of the order of H gets you to the order of G. And it's exactly the number of cosets. So in order to get there, well, we have to know what cosets are, right? So it always starts with some subset of G, or subgroup of G, sorry. So if you start with the subgroup H, then the left cosets are things of the form AH, which just means basically you run over all products of the form A times little h, where little h can be anything in H. Right, so we're going to do some examples here in a second, but like this in general is not a group. Okay, it's just a set inside your group. It is running over a lot of products, but for instance, only one of your distinct cosets will contain the identity. So like most of them are not groups, but as you did see, we can think of them as like clones, right? If you looked in that Cayley graph in our example, then you kind of saw all of the cosets looked the same. They were kind of just moved around the Cayley graph, but they all looked like copies of each other. And that's basically what's going to happen. Okay. And then your right cosets, well, it's just the same thing, except you multiply on the right instead of the left. And so it's HA. In general, as you saw in our example, right, so we looked at G was D3, and H was a subgroup generated by S, then you saw that the left may not be the same as the right. Hopefully, we noticed that. We'll check the right in a second, but basically our left cosets, right, were ES, which is H and SH. We got R and RS, which is RH and RSH, and then we got R squared and R squared S, which is R squared H and R squared SH. And again, let's look back up at Lagrange's theorem, right? So 1, the order of H is 2, it definitely divides 6. But then when I divide that, I get the number of cosets. I got exactly 3 cosets here. 6 divided by 2 is 3. So this is kind of showing you by example, hopefully that you get a little intuition for what's going on there. And also note that all of these cosets have the same number of elements in them, right? They all have 2 elements, which is the number of elements in H. All have order of H elements. Because that's going to be basically another key ingredient to our proof, that they all have the same order. Okay, so let's look at the right cosets. So you just kind of have to go through it, right? So I mean, this is ES, and so you just kind of multiply. So it should be clear that anytime you multiply by things in H, right, so E and S themselves, that you're going to get H back. That's just closure, right? H is a subgroup. So since E and S are in H, EH equals H equal, or sorry, well, I mean, that's also true, but I want the right cosets. This will always be the case. If you multiply by some element in H, it's just going to stay that same coset you started with, okay? It'll just be the subgroup. But then, once you get outside of the subgroup, you don't have a notion of closure anymore, and so you actually have to like think about it and check. So what is HR? Well, so it's going to be ER and SR, which, of course, that's R, and then SR is the same as R squared S, right? So this is different, right? Here, for R, we had RS, not R squared S, and here we have R squared S, but then we had R squared, not R. So this is not the same as any left coset. And so we do actually get something different here. Okay, well, so first of all, these should be the same thing as well. So let's check that H times R squared S actually gets us the same thing. Because we noticed that over here, right? Like RH and RSH, well, these were the two elements in here. And so we should see the same pattern over here. So let's see that checks out. Okay, so we get E and R squared S. So yeah, that works. And then we get S R squared S. Well, the first one's definitely R squared S. And then S R squared S is, well, again, R squared S is SR. So this is like SSR, but then S squared is the identity. So this is R. And so these are the same. And this is what we would hope for, right? Because we want only 3 distinct ones. Because I kind of told you that it shouldn't matter if it's left or right up here. I said left, but basically it won't make a difference. It's just that we typically multiply things on the left in our lives and we read left to right, and so that's just kind of like the way we do it, but we could do everything with right cosets if we wanted to. And so then the last one here is HR squared, which is the same as HRS, which contains exactly R squared and RS. And again, this is also not a left coset. So the point is you can get different left cosets and right cosets. Sometimes they are equal, and we'll see that this is actually a very important notion. So that'll be kind of one of the things we kind of end this chapter with, and that will help us develop kind of a notion of division in groups. Yeah, any questions on this before we do a couple more examples? You just kind of have to get used to the notation and terminology with cosets. I think it's just different than what we've done so far. But as of right now, it's really just multiplying. So is H always that? No, by no means. So this was just one example. So, I mean, I could have called the next one H as well. In 5.3? Yeah, but I called it K. But no, you can do it for any subgroup. So you do fix a subgroup to start, but you can fix whatever subgroup you want, right? So like I could look at D3 again, but not with the subgroup generated by S, but instead the subgroup generated by R. Now, I saw a lot of mistakes when looking through this for the people who kind of turned this in early. I think we were trying to base a little too much off of the first example. The subgroup generated by R is not 2 elements, right? This is E, R, and R squared. So this should have 3 elements. So given that, let's travel back up here. Let's not travel that far. All right. So 3 elements. So this time, right, I had like a k. And I know that this should divide g, and it does, right? So 3 definitely still divides 6. But now, how many cosets should I have in this case, if the order of k is 3? I should only have 2 cosets, right? I should have 6 divided by 3. So here we would expect to have 2 cosets. So if we looked at our left, well, again, 3 of them are going to be the same, and you should know this right off the bat, right? So if I multiply by any of these 3 elements, k is closed. It's a subgroup. So I'm going to stay in there, right? So ek is rk is r squared k is just k. Always going to be true. And then our other one, and probably suffices to actually check. So sk, well, we get es, which is s. We get sr, which is r squared s. And then we get sr squared, which is rs. So we get these 3 elements. And notice that these were all the rotations. These are all the reflections. Kind of cool how it partitions them exactly due to their like different geometry, right? And if you look through, so like rs, k is rs, rsr, but sr is r squared s, so this is just s. And then you get rs, r squared, sr squared is rs, so this is r squared s. That's the same, and then you can check, but this guy is also equal to sk and rsk. So you get 2 distinct cosets. One with the 3 reflections and one with the 3 one with the 3 rotations, one with the 3 reflections. And so when doing this one, so again, your right one, well, the first part's still going to be the same, right? Like whether I multiply on the right or left, it's closed either way. So this is still going to be true since k is closed. It's a subgroup. And you would again see that ks, krs, and kr squared s will still give you all the reflections. So in this case, my left cosets equaled my right cosets. And it turns out there's something special going on here, and it's the fact that there are 2 cosets. Essentially, if you have a subgroup that takes up exactly half of your group, then it's always going to have this property, that the left cosets are equal to the right cosets. So another example would be an inside Sn. So the order of Sn over the order of An is equal to 2. And so again, you would basically think that there are 2 cosets, and it is true. And basically, you're going to get the cosets of, they'll give you 2 sets, the odd permutations and the even permutations. So I'm not going through the details of this yet. This is something, again, I may leave to the problem set with An just to kind of think through this a little bit more, but just kind of a preview. So this is an important one, and again, this is because we know that this is n factorial over 2 here. But I'm really kind of applying Lagrange's theorem a little bit before I've really proven it, but I'm kind of showing why it may be useful. Okay. Let's see. So we can talk about this a little more, actually. So what if I do this? So I don't think this one needs to be a problem set. So if I have An, and then I look at the coset sigma times An. So An is the set of all even permutations, right? I was just kind of looking at the time and seeing how much we have left. I think this is useful to actually just go through since we started it. And then this will kind of be what we finish up with. So if I have something on the left that is even itself, what do I get back? So if I multiply an by some single even permutation, what set will I get back? Remember how we defined an to be the set of even. Yeah, exactly. It's still the set of evens, right? It's an even times an even. So this is an. Again, since an is closed, right? So if sigma is even, sigma is in an. So you get an back. Okay. What if sigma is odd? Well, the point is, an odd times an even is always odd, right? Odd times even equals odd for any odd. So basically, what I'm saying is sigma an equals tau an equals the set of odd permutations. I can just leave this part out, to be honest. I was going to say, like, you can do any of the two, but this is just a stronger statement. So sigma times an is the set of odd permutations if sigma is odd, because you just multiplied an odd guy by all of these even guys, and every one of those products will now be odd, because odd plus even is odd. And so basically, I've broken it down into two cosets. An, and then you can do, for instance, like 1, 2 times an, and the point is this is the set of odd permutations. Okay? And these are exactly your two left cosets, but you should realize, right, that like this argument had nothing to do with it being on the left or the right, because we don't care in which way we add, right? Like an odd plus an even is the same as an even plus an odd. And so an and an times 1, 2, same breakdown for right cosets. So that's pretty cool. Okay. And in this case, all of your left cosets would be equal to your right cosets, because they are exactly either the evens or the odds. Okay. All right. Yeah, I will be around. Again, if you're working on things, feel free to ask questions on daily homework stuff too, if you're working through those. But I'll be around for a little bit after class, and then, I have office hours later this afternoon. Okay? So have a delightful day.